Isolation transformers are indeed required in hospital operating rooms, even if flammable anesthetics are not in use. The primary reason for this requirement stems from stringent electrical safety standards designed to protect patients and medical personnel from electrical shock hazards. These standards are in place to minimize the risk of macroshock and microshock. Macroshock refers to the electrical shock that occurs when a relatively large current passes through the body, typically entering through the skin and exiting through another point on the body. Microshock, on the other hand, involves a very small current, often in the microampere range, directly entering the heart through a conductive pathway, such as a cardiac catheter or pacemaker lead. Because patients in operating rooms are often particularly vulnerable due to anesthesia, open wounds, and the presence of conductive medical devices, the risk of both macroshock and microshock is significantly elevated. Isolation transformers play a critical role in mitigating these risks by creating an ungrounded electrical system. In a grounded electrical system, if a fault occurs, such as a wire coming into contact with a grounded surface, a large fault current will flow to ground. This high current can trip a circuit breaker or blow a fuse, effectively shutting off the power to the circuit. While this is a safety feature designed to prevent fires and electrical hazards, it can also create a dangerous situation in an operating room if the power is suddenly interrupted during a surgical procedure. An ungrounded system created by an isolation transformer operates differently. In an ungrounded system, a single fault to ground will not cause a large current to flow or trip a circuit breaker. Instead, the system will continue to operate, albeit with a slightly elevated voltage to ground on the unfaulted conductors. This allows the surgical procedure to continue without interruption while also providing an indication that a fault has occurred. The presence of a line isolation monitor, often referred to as an LIM, is crucial in an ungrounded system. The line isolation monitor continuously measures the impedance from each line conductor to ground. If a fault occurs, the impedance will decrease and the line isolation monitor will alarm, indicating that a fault is present and needs to be addressed. This alarm provides a warning that the system is no longer operating under ideal conditions and that a second fault could create a shock hazard or interrupt the power. The National Electrical Code, specifically Article 517, addresses the electrical requirements for healthcare facilities, including operating rooms. Article 517.20 specifically mandates the use of isolation power systems in anesthetizing locations. These locations are defined as areas where patients are administered inhalation anesthetics. While the original intent of this requirement was to prevent explosions caused by flammable anesthetics, the requirement remains in place even when flammable anesthetics are not used due to the increased risk of electrical shock in these environments. It is important to note that the use of isolation transformers and line isolation monitors is just one component of a comprehensive electrical safety plan for operating rooms. Other important measures include regular testing and maintenance of electrical equipment, proper grounding of equipment, and the use of ground fault circuit interrupters or GFCI devices in wet locations. The purpose of these measures is to minimize the risk of electrical shock and ensure the safety of patients and medical personnel. To further elaborate on the functionality of the line isolation monitor, it does not prevent a first fault. Instead, it measures the total hazard current, which includes leakage current and resistive fault current. The line isolation monitor alarms when the total hazard current exceeds a predetermined level, typically 5 milliamperes. The alarm indicates that the system is no longer operating under normal conditions and that a potential shock hazard exists. The alarm also provides an indication that the system should be inspected and the fault located and corrected. The requirement for isolation transformers in operating rooms is not solely based on the presence or absence of flammable anesthetics. It is primarily driven by the need to protect patients from electrical shock hazards in an environment where they are particularly vulnerable. The use of isolation transformers and line isolation monitors creates an ungrounded electrical system that minimizes the risk of macroshock and microshock. The National Electrical Code, specifically Article 517, mandates the use of isolation power systems in anesthetizing locations. These systems include isolation transformers, line isolation monitors, and other components designed to enhance electrical safety. Regular testing and maintenance of these systems are essential to ensure their continued effectiveness. In summary, the use of isolation transformers in hospital operating rooms is a critical safety measure that is required by the National Electrical Code. The primary purpose of this requirement is to protect patients and medical personnel from electrical shock hazards. Even when flammable anesthetics are not used, the increased risk of electrical shock in the operating room environment necessitates the use of isolation power systems. These systems provide an ungrounded electrical supply that minimizes the risk of macroshock and microshock, ensuring a safer environment for surgical procedures. Healthcare facilities must adhere to these codes. It is important to note that even though isolation transformers are not a substitute for standard safety practices, they are an additional layer of protection in the operating room. These safety practices include ensuring that all electrical equipment is properly grounded, using ground fault circuit interrupters in wet locations, and performing regular maintenance on all electrical systems. The isolation transformer isolates the operating room's electrical circuits from the main electrical supply, preventing a direct path for electrical current to flow to ground through a patient or staff member. The line isolation monitor detects any leakage current in the isolated circuit, alerting staff to potential faults that could pose a shock hazard. The combination of these two components significantly reduces the risk of electrical shock in the operating room. There are a few different types of isolation transformers, but they all serve the same basic purpose. The most common type of isolation transformer is a single-phase transformer, which is typically used in smaller operating rooms. Three-phase transformers are used in larger operating rooms that require more power. No matter what type of isolation transformer is used, it is important to ensure that it is properly installed and maintained. The National Fire Protection Association, or NFPA, also publishes standards related to electrical safety in healthcare facilities. NFPA 99, Standard for Healthcare Facilities, provides requirements for electrical systems in hospitals, including operating rooms. NFPA 99 reinforces the need for isolation power systems and provides guidance on the installation, testing, and maintenance of these systems. Healthcare facilities should consult both the National Electrical Code and NFPA 99 to ensure compliance with all applicable electrical safety standards. Periodic testing is very important. Regular testing of the isolation power system is essential to ensure that it is functioning properly. The National Electrical Code and NFPA 99 provide guidelines for testing procedures and intervals. Testing should include verifying the proper operation of the line isolation monitor, measuring the leakage current in the isolated circuit, and inspecting the transformer for any signs of damage or deterioration. Any deficiencies identified during testing should be promptly corrected to maintain the safety of the operating room environment. Understanding the electrical distribution system in a hospital operating room requires a grasp of key components and their roles. The main electrical service enters the hospital and is distributed through a series of panels and transformers. The operating room receives its power from a dedicated isolation power system, which includes the isolation transformer and line isolation monitor. The isolation transformer creates an ungrounded electrical supply, while the line isolation monitor continuously monitors the system for faults. Electrical outlets and equipment in the operating room are connected to the isolated power system. To summarize, the isolation transformer requirement in operating rooms is not solely dependent on the use of flammable anesthetics. It is a fundamental safety measure mandated by the National Electrical Code and reinforced by NFPA 99. The purpose of this requirement is to protect patients and medical personnel from electrical shock hazards in an environment where they are particularly vulnerable. Isolation transformers create an ungrounded electrical system, while line isolation monitors detect an alarm for potential faults. Regular testing and maintenance are essential to ensure the continued effectiveness of these systems. By adhering to these standards and best practices, healthcare facilities can create a safer environment for surgical procedures. The electrical safety standards in operating rooms are constantly evolving. As new technologies and medical devices are introduced, the standards are updated to reflect the latest knowledge and best practices. Healthcare facilities should stay informed about these changes and ensure that their electrical systems are compliant with the most current requirements. Consulting with qualified electrical engineers and healthcare facility professionals is essential for maintaining a safe and reliable electrical environment in operating rooms. Furthermore, consider the practical implications of an ungrounded system. While a single fault won't immediately shut down the power, it's crucial to locate and correct the fault promptly. Ignoring the alarm from the line isolation monitor can lead to a more dangerous situation if a second fault occurs. The presence of two simultaneous faults in an ungrounded system can create a direct path for current to flow, resulting in a shock hazard that could have been avoided. Therefore, healthcare facilities must have procedures in place for responding to line isolation monitor alarms and for troubleshooting electrical faults in a timely manner. Staff training is also important. All personnel working in operating rooms should receive training on electrical safety procedures, including the operation of the line isolation monitor and the proper use of electrical equipment. Staff should be aware of the potential hazards of electrical shock and should know how to respond in the event of an electrical incident. Regular training and refresher courses can help to ensure that all staff members are knowledgeable about electrical safety practices and are prepared to handle any situation that may arise. The location and placement of the isolation transformer is also a design consideration, which should be readily accessible for maintenance and inspection. It should be installed in a clean, dry environment and protected from physical damage. The transformer should be properly sized to meet the electrical load requirements of the operating room. Overloading the transformer can lead to overheating and failure, potentially creating a fire hazard. It's also important to consider the grounding of the isolation transformer. While the secondary side of the transformer is ungrounded, the transformer itself must be properly grounded to the building's grounding system. This grounding provides a path for fault current to flow in the event of a primary side fault, helping to protect the transformer and prevent electrical hazards. In addition to isolation transformers, other electrical safety devices may be used in operating rooms, such as ground fault circuit interrupters and isolated power panels. Ground fault circuit interrupters are designed to detect small leakage currents to ground and to quickly interrupt the circuit, preventing an electrical shock. Isolated power panels provide a dedicated source of power for sensitive medical equipment, isolating it from the main electrical system. These devices can provide additional layers of protection in the operating room environment. To recap, the purpose of isolation transformers in hospital operating rooms is to create an ungrounded electrical system, minimizing the risk of electrical shock to patients and medical personnel. This requirement is mandated by the National Electrical Code and reinforced by NFPA 99, even when flammable anesthetics are not in use. The line isolation monitor continuously monitors the system for faults, and regular testing and maintenance are essential to ensure its continued effectiveness. By adhering to these standards and best practices, healthcare facilities can create a safer environment for surgical procedures. Consider a scenario where a piece of medical equipment develops a fault, causing a small leakage current to flow to ground. In a grounded electrical system, this leakage current could flow through the patient, creating a shock hazard. However, in an ungrounded system with an isolation transformer, the leakage current will not flow through the patient. Instead, the line isolation monitor will detect the fault and alarm, alerting staff to the potential hazard. This allows the staff to address the fault before it can cause harm to the patient. Think about power quality. Isolation transformers can also improve power quality in operating rooms by filtering out noise and harmonics from the electrical supply. This can help to ensure that sensitive medical equipment operates reliably and accurately. Power quality is particularly important for equipment that relies on precise voltage and current levels, such as surgical lasers and imaging systems. By providing a clean and stable power supply, isolation transformers can enhance the performance and lifespan of these devices. Discussing future trends, advancements in electrical safety technology are constantly being developed. New types of isolation transformers, line isolation monitors, and other safety devices are being introduced to the market. These new technologies offer improved performance, reliability, and ease of use. Healthcare facilities should stay abreast of these advancements and consider incorporating them into their electrical safety plans. Consider the cost implications of isolation transformers. While isolation transformers represent an upfront investment, they can save healthcare facilities money in the long run by preventing electrical accidents and equipment damage. The cost of a single electrical shock incident can be significant, including medical expenses, legal fees, and lost productivity. By investing in isolation transformers, healthcare facilities can reduce the risk of these incidents and protect their financial resources. In addition to the National Electrical Code and NFPA 99, other standards and regulations may apply to electrical safety in operating rooms depending on the jurisdiction. These standards may cover topics such as the installation of electrical equipment, the use of personal protective equipment, and the training of electrical workers. Healthcare facilities should be aware of all applicable standards and regulations and should ensure that they are in compliance. Consider the role of healthcare facility managers in ensuring electrical safety in operating rooms. Facility managers are responsible for overseeing the maintenance and operation of the facility's electrical systems. They should work closely with electrical engineers and healthcare professionals to develop and implement a comprehensive electrical safety plan. They should also ensure that all staff members are properly trained on electrical safety procedures. Consider the importance of documentation. Healthcare facilities should maintain detailed records of all electrical equipment, including isolation transformers, line isolation monitors, and other safety devices. These records should include information on the installation, testing, maintenance, and repair of the equipment. Proper documentation can help to ensure that the equipment is properly maintained and that any problems are quickly identified and corrected. In summary, the use of isolation transformers in hospital operating rooms is a critical safety measure that is required by the National Electrical Code and reinforced by NFPA 99. The primary purpose of this requirement is to protect patients and medical personnel from electrical shock hazards. Even when flammable anesthetics are not used, the increased risk of electrical shock in the operating room environment necessitates the use of isolation power systems. These systems provide an ungrounded electrical supply that minimizes the risk of macroshock and microshock, ensuring a safer environment for surgical procedures. Healthcare facilities must adhere to these codes. It is important to note that even though isolation transformers are not a substitute for standard safety practices, they are an additional layer of protection in the operating room. These safety practices include ensuring that all electrical equipment is properly grounded, using ground fault circuit interrupters in wet locations, and performing regular maintenance on all electrical systems. It is crucial to remember that electrical safety is an ongoing process. Healthcare facilities must continuously monitor their electrical systems, train their staff, and stay informed about the latest standards and technologies. By taking these steps, they can create a safer environment for patients, medical personnel, and visitors. Think about the specific needs of different types of operating rooms. For example, operating rooms used for cardiac surgery may have different electrical safety requirements than operating rooms used for orthopedic surgery. The electrical safety plan should be tailored to the specific needs of each operating room. Always consider the human factor. Electrical safety is not just about technology, it's also about people. Healthcare facilities must create a culture of safety in which all staff members are aware of the potential hazards of electrical shock and are committed to following safe work practices. This culture of safety should be reinforced through training, communication, and leadership. Lastly, remember that electrical safety is a shared responsibility. All stakeholders, including healthcare facility managers, electrical engineers, healthcare professionals, and staff members, must work together to ensure a safe electrical environment in operating rooms.